Okay, let's consider a system of equations like this one. Now, in the past, you've encountered systems like this, and you've learned techniques to solve them. Maybe substitution or elimination. Now, this elimination method, remember what was involved in the elimination method. We would eliminate one variable. Maybe I would multiply equation 1 by -3, and then I would add it to this equation 2 down here, and what we would have is -3x, add it to 3x, and the x's would be eliminated. Remember, that's what happened with the elimination method. So we're going to kind of build on that and see if we can proceed with the elimination method, but in a more structured way. In other words, let's rewrite this system of equations in matrix form, like this. See, notice what I have here. I have a coefficient, a matrix of coefficients, right? See, 1x, 2y, 1x, 2y, 3x, 5y, see? And then over here on this other side, I have the constants, 8 and 21. Now, just to see how this represents the same thing. In other words, this matrix equation here conveys the same information as this system up here. Notice, if I were to multiply this coefficient matrix by this xy here, I would get 1x plus 2y equals 8. And then down here, 3x plus 5y equals 21. In other words, if you were to multiply this out, you would get this back. So it conveys the same information. Now, I want to do some work with this matrix or this little equation here, and I don't really need this xy there. I'm just going to remember, okay, I have a variable. This is the x column, and this is the y column. So I'll just keep that in mind, and let me take out this whole matrix right here and rewrite this whole thing here this way. And I just understand that this is the column of the x's and this is the column for the y's. I've got 2y, 5y, 1x, 3x, and then equals 8 and 21 over here. Okay, now what I want to do is what you would do if you were using the elimination method. I want to take this row 1 and multiply it by -3 and add to row 2 because I want to eliminate this number right here. I want this to go to 0. This is called a row operation. Now, after I get finished multiplying this first row by -3 and adding to the second row, I'm going to put row 1 back like I found it. I'm just using it to eliminate that number down there to make it go to 0. And I'll denote it this way. -3 times row 1, add it to row 2, and I get this matrix. Notice what happens. -3 times 1, add it to 3, I get a 0. -3 times 2 is -6, add it to 5, I get a -1. -3 times 8 is -24, add it to 21, I get a -3. So this is my new matrix. Now, look at this. We start off with 1x plus 2y equals 8, right over here. 1x plus 2y equals 8. 3x plus 5y equals 21. Now let's see what we've got. 1x plus 2y equals 8. And look down here. -1y equals -3. Well, we're ready at this point to identify what y is. But let me just go one more step. Let me go ahead and divide out the -1 here, or multiply through by -1. And I get this new matrix. Now, dig what we have here. We have 1y equals 3 on this second row. In other words, this is what we have. Okay? Now, if I know that y equals 3, I can substitute back in and find out what x is. See, because we have x plus 2y equals 8. So I get x equals 2. Ah, look at that. We have found the solution to that system. And the method that we used here, it was really elimination, right? But the process that we went through, we used these row operations. This is Gaussian elimination, okay? Gaussian elimination. And you can see this is the intersection here. We've got our two lines, and then you can see what we found successfully was that point of intersection. Now, sometimes you'll encounter a system of equations like this one where there is no solution. Let's see what that would look like if we use the Gaussian elimination. So we start off here with this one. I put my coefficients in here, and I start my operations. I multiply row 1 by -3 and add to row 2. Now, you notice when we do that, here's what we get. We get the first of all, row 1 doesn't change, but look down here. We get 0 and 0. See? -3 times 1, add it, 0. -3 times 2, -6, add it. We get 0 there. So now look what happens. We've got down here, up here is x plus 2y equals 8. But down here, 0 equals -10. Well, that doesn't make any sense. 0 is never going to equal -10. So what this indicates is our system has no solution. When you get some nonsense like that, you're thinking, this system has no solution. And if you look at the graph, you can see, it looks like these lines are parallel. Now, if you solve them, well, let's look at that. There's the lines. There's the purple. Now, if you were to solve these for y, you would find that both of them have the same slope. Okay? So it looks like both of them would have a slope of -1/2 if you solve them. They have different y-intercepts, but the same slope. So that system had no solutions. Now let's look at another system, this one. And let me go ahead and put it in matrix form. Here we go. Now notice, let's look at this. We've got x plus 2y equals 8. 1, 2, 8. Now let's suppose I multiply this first row by 3. Look what happens. 3 times 1 is 3. 3 times 2 is 6. 3 times 8 is 24. Look at this. This second equation is just a multiple of the first. This second row is 3 times the first row. Whenever you see something like that happens, it means that really you're dealing with the same line here. Notice, if I just multiply if I divide through by 3, I get x plus 2y equals 8. So this equation is just a multiple of this one. It's just acting like it's a different line, but it's the same line. But let's see what happens when we go through this process of elimination. Let's suppose we didn't notice that one is a multiple of the other. So I'm going to multiply row 1 by -3 and add to row 2. And here's what we get. Look at this. 0, 0. Now, unlike the last example, this is always true. 0 always equals 0. The other one was 0 or a number equals 0 or something like that. Well, it was 0 equals a number, but this one, 0, 0. Well, that's always true. So what we have here, this is, when we get something like this, this tells us, we have a dependent system. We really are dealing with the same line here. And in fact, if you solve this equation for y and put it in slope-intercept form, both of these, if you do this one or this one, what you're going to get is -1/2 x plus 4. So that's a dependent system. Now let's look at planes. Here's a 3 by 3 system. So we don't just have x and y, we have z. So these are 3 different planes. And what we're wanting to do is find that point that all 3 of these planes contain. The one point these 3 planes have in common. So I put it in matrix form. Okay? Here it is, matrix form, and I start my operations here. Now, first thing I want to do is I think I want to get a 0 here. So here's our goal. Let me just state what our goal is. Our goal is to get a situation where we can identify, you'll see it more clearly as we get through this, but my goal is to just get a number here. Okay, on this last, I want 0 here and 0 here, and I want a number here because when I have a number here, I'll be able to solve for z. And then if I can solve for z, I can come back up here and solve for y. So here's what I want to happen. I want, in this Gaussian elimination, I want to get a 0 here and here and here. because then I can solve for z, and then I can back substitute and solve for y, and then back substitute and solve for x. Okay, so I think as you see the process, you'll understand what our goal is. First thing I want to do is get a 0 here. So I'm going to multiply row 1 by 3 and add to row 3. See, like this. And there's what I get. Now let's take a minute and dig what's happened. 3 times 1 is 3. Add it to negative 3. I get a 0. Good. 3 times 1 is 3. Add it to 2 and I get a 5. 3 times 1, add it to 1, I get a 4. And finally, 3 times 9 is 27. Add it to 4 and I get a 31. Okay, so I've got a 0 here. Great. Now I want to get a 0 here as well. And then I want to get a 0 here, and then I'm done. So let's look at this. To get a 0 here, I need to multiply by negative 2 and add. So I'm going to take this equation, or this row 1, multiply it by negative 2 and add to row 2. And here's what I get. So dig what happened. Negative 2 times 1 is negative 2. Add it to 2, 0. Negative 2 times 1, add it to 1. I get a negative 1. Negative 2 times 1, add it to negative 2. I get a negative 4. And finally, negative 2 times 9, I get a negative 18. Add it to negative 1, negative 19. So look what I have now. I have a 0 here and here. I need a 0 here now, and then I'll be set. That's our goal. When we do this elimination, that's what we're going for, because we want to do a back substitution. Okay, so here we go. Now, I want to get rid of this one, so it seems like an obvious choice would be to multiply row 2 by 5, see, to get rid of that 5, and add to row 3. So let's see what happens. Okay, here we go. Now, 0 times 5, it's not going to do anything. It's just going to give me 0. Now, negative 1 times 5 is negative 5, so add there and I get a 0. Bingo, that's what I wanted. Now, negative 5 times negative 4 is negative 20. Add it to 4, negative 16. And finally, negative 5, or 5, multiplied by negative 19, I get, and then add it to 31, I get a negative 64. Okay, so 5 times negative 19, add it to 31, and I get a negative 64. Now, this is what we want, because look what we have now. We have x plus y plus z equals 9. Negative y minus 4z equals negative 19. And down here, negative 16z equals negative 64. Well, that immediately tells me that z equals 4, because I can divide. Ah, excellent. Now I can go back and say, okay, what about here? Negative y minus 4z equals negative 19. Well, I can put in the negative 4, I can put in the 4. See, just put in a 4 right here, and I get y equals 3. Well, now I know what y and z are, so now I can figure out what x plus y plus z equals 9, what x must be. Just plug in 3x plus 3 plus 4 equals 9, and I get x equals 2. So here is our point of intersection. This is the point at which these 3 planes intersect. And a picture of it would look like this. Okay? So we've got our 3 planes here. You've got the pink one right here. Okay? This one. You've got the red one, and then the green one. And right there is the point of intersection. I don't know if this picture is very helpful, but you can see what's going on with this. Okay? So that's how we found that point of intersection, by Gaussian elimination, going through this process, the row operations, the elementary row operations. Now let's look at this one. This is interesting because this is a system with 2 equations and 3 variables. Notice we had a system with 2 equations and 2 variables, a system with 3 equations and 3 variables, but now we have too few equations, it seems. So we have these 2 planes, and I wonder what's going to happen. Well, let's see. Let's put those in our matrix, in a matrix form. So we have 1, 1, 1, 1, and then 2, negative 1, 1, 2. Okay? start our row operations. I need to get rid of this 2. So multiply this by -2 and add. And I get a 0. See, -2 plus a -1, -3. -2 plus 1, -1. And -2 plus 2, 0. Okay, there's what I have so far. Now, we're at a point where we can't, I really don't need to go any further. I'm really about to do this is about the best I can do with this, because notice what I've done here is really I've eliminated the x down here, and here is what I have. I have -3y minus z equals 0. Okay? That means that y is equal to -1/3 z. Okay, now, here's the game I'm playing. I'm saying, okay, well, z is equal to itself. Z is just z. So what I'm going to do is I'm going to say, okay, I can't find a unique point of intersection. It looks like what happens is these planes intersect in a line. And what I'm doing is I'm constructing a solution that's all dependent upon my choice for z. So in other words, if z is equal to itself, y is equal to -1/3 z, and then I've got this. I've got x plus y plus z equals 1. Well, that means that x plus y, that's x minus 1/3 z, because that's what y is, plus z equals 1. That means that x equals 1 minus 2/3 z. Yeah. So let's look at what our solution would be. X is 1 minus 2/3 z, y is -1/3 z, and of course z is z. Now we could say, well, let z equal a. And then we would have a solution that looks like this. But here's the thing. These two planes don't intersect in just a unique point. They intersect in a line. These two planes come together, and there's a line formed where they intersect. And if we want a particular solution, a particular point on this line, all I've got to do is assign a value to z. For example, I could say, or a in this case, let a equal -3. So I want to know, okay, what is the point that corresponds to the z-coordinate being -3? And it would be this, see? I just put a -3 in place of the z's. And I get this. This is the point of intersection that corresponds to the z-coordinate being -3. So if we look at this on a graph, notice we've got the two planes, they intersect here, and then we've got this one point down here of intersection. See, I've got the 2x minus y plus z equals 2 plane, and then I've got the x plus y plus z equals 1 plane. See, those two planes. And look at this intersection here. See that line where they come together? Yeah. Here is the particular point. When I let a equal -3, that's that point. Now, I can generate solutions all day, for points on this line of intersection. But this is the best we can do with this. There's not a unique point of intersection.